This is a work-through solution for question 6.7 in the workbook, which is a sort of multi-step heat engine question. And although the latter parts are a little bit more involved, I guess the first sort of parts A, B and C is something that could typically come up in an exam, or that sort of standard, that sort of level. Right, so reading the question out, should appear above me. We have a 4-stroke spark ignition engine, the compression ratio of 9, and it's an Otto cycle, so standard car petrol engine. We're given a couple of values, P1 and T1, and also we're told the amount of heat that moves between along process 2, 3. Right, to start off we need to draw, so part A is to draw out the Otto cycle in pressure, volume and temperature entropy space. Now this is, I guess the Otto and diesel cycle, maybe the Brayton cycles, are useful ones to sort of remember for an exam, and to be able to plot out the 4 simplified processes and label them up and understand this is sort of integral to the whole part of the module dealing with gas laws and heat engines. Right, so and the useful thing with these as well, you only have to remember 2 processes because obviously they're equal and opposite. So we'll start, as we always do with engines, with the compression part. Point 1. So we're going to compress the gas, and with the Otto cycle we have 2 adiabatic processes, which are the work processes, and 2 isochoric processes, which are the heat addition and rejection. So obviously starting down here at the intake, so this is our sort of starting point. As we'd expect, we've not done anything yet, so we've got high volume and low pressure. And we have a diabatic compression. Point 2. We can draw this in TS space as well. So why am I down here? Well, we've not put any heat in yet, so the entropy, the ability or propensity to lose useful work is low. Okay, so we're going to be down this part of the diagram. And again, it's a diabatic. We've gone up in temperature because we've compressed the gas fairly rapidly. Up to point 2. Okay, so back to PV space. Our isochoric heat addition, so Q in. Diabatic work process now to get work out of the gas. Got the best drawing ever. 0.4. And then our heat rejection here. Okay, fairly standard stuff. Again, 2 equal and opposite work processes, and the same with the heat. And again, we can work out the work done, each of these processes, because it's the area under the process line. And then take one away from the other, work out minus work in, leaves us with the calculated area inside this 4-process cycle. Okay, and that's the net work done. Okay, so in temperature entropy space, again just sort of completing the diagram. Okay, so you can see obviously they clearly start in different places because we're in a different sort of gas energy plane, if you will. But this is a sort of useful thing to be able to, I guess, remember and recall for an exam. So when you see the word Otto cycle, you can immediately think, okay, 2 adiabatic processes and 2 isochoric processes. So that's part A done. Right, okay, for part B, we need to find the pressure at point 3, up here. Okay, and there's 2 methods we're going to use. First method is using the ideal gas law equation, so PV equals RT, to find properties of state at a point. Okay, and the second one is to use the process equations for these to be able to move from one point to another. Okay, so for example, we know process 1 to 2 is a diabatic. So if we know some of the properties at point 1, we can calculate them for point 2. Anything with sort of isochoric or isobaric processes, again, you've got constants in pressure or volume as well, so they're quite quick things to tick off. But we need to find a starting point and traverse around this diagram to get P3, which is the end goal of this part of the question. This is what we've been given in the question. When you look at it on screen, it doesn't look like very much information is given, but we've got enough to make a start. Again, you have to combine that information with your knowledge of what an Otto cycle is and how it looks, what processes are used. You've got no clue, and this is modelled using an Otto cycle. It doesn't tell you that it's 2 adiabatic and 2 isochoric processes, then you're pretty stuck. Okay, we're given T1, again, always in Kelvin. P1, which is 1 bar. So we know now down here we're at 1 bar. We're given the amount of heat put into the cycle, 2000 kilojoules per kilogram, and we're given the compression ratio, which is V1 over V2 equals to 9. So we can find out one of the V's, we can work out the other, okay, because we know the ratio between the 2. So we'll start off. We've got an in for this question, and that's at point 1 because we've given P1 and T1, so we can find out V1. And again, just using the equation, P1, V1 equals R, T1. And that value of R is 287. It's the general gas constant. So we're not looking at the alternative, which is the NR version. Okay. Right, so we can rearrange this to find V1. So P1 is 1 bar, so 1 times 10 to the 5. R is 287, T is 288 degrees Kelvin. So work that through. P1 6. And then we can obviously work out V2 from this ratio. Right, so now we have all the properties of state at point 1. Next step is to use the equation that we know relates point 1 to point 2 because it's an adiabatic process. Right, so we can now write V1, V1, Okay, well this is 1.4, the ratio of the specific heats. We know P1, V1, we know value of gamma. We also know P2, so we can solve, V2, so we can solve the pressure at point 2 now. Okay? So we have to rearrange that equation. Now we get value of P2 of 21.7 bar. Okay, so now we've got, starting to get some information at point 2. Right, the next stage we can now use is to look at this process of the heat in from 2 to 3. So we can now start moving up into this top corner. You notice we don't have to go via point 4 for this question, because we're going to work our way around clockwise. Okay? So we have some information now about the amount of heat put in between point 2 and 3. Okay, so that's our next step. Right, okay, I've just written out the properties of state that we've worked out so far. So T1 and P1 given in the question. We worked out V1 through the equation of state, and then the ratio to work out V2. And we worked out P2 with this equation defining a diabatic process. One thing we need to do quickly is to work out another. We know this is constant volume heat addition, okay? So we can write Q2 to 3 equals CV T3 minus T2. Okay, we need to work out T2 quickly. So you can, again, we know P2 and V2, so you can use the ideal gas equation to quickly work out T2. And just for reference, that's 695 Kelvin. Okay, now rearranging this, we can work out T3. So I'll write this one out. T3 equals Q23 CV times T2. So working out through, so it equals 2000 CV, which in this case is 0.725 plus our 695. Hopefully I'm not off the screen there. So then we get a value of T3 equals 3,454 Kelvin, so reasonably hot. Okay, so adding to our list now, we now know T3. And we're almost there. Right, last little hop. We need to find P3 for this part of the question. Very close. We know V2. V3 is obviously equal to V2. So we can tick off V3. Now we can just write P3 V3 equals RT. Okay, and then the only unknown is P3, which, for sake of completeness, equals 107 bar. Okay, and that's part B finished. You can work quite quickly at this. It's just two simple rules just to work around, and we got some free hits with volume ratios and the fact that we've got some isochoric processes as well, so that speeds things up a little bit. But you can see it's just a nice methodical plod around the PV diagram for that one.